Good afternoon. Let us continue our discussion last Monday. So what we have from last Monday is BUV, which is a bilinear form, right? Bilinear mapping of form or bilinear form. So this bilinear mapping is bounded in the sense that you take the absolute value of this is going to be smaller than the norm of u times the norm of v, right? And we are considering u and v in the Hilbert space H, right? So this is norm in H, which is L2 in our case, right? And then this is coexistive. So this bilinear form is called coexistive, meaning that if you take v is equal to u, then you're going to have that BUU is going to be bigger than beta u squared. So we consider L, which is in H star, right? So which means that this is a linear form, a linear mapping. So L is linear mapping. From H to R, right? So you take a U in H, and LU is a number in R, right? So this is the what we hypothesis on beta on B, and this is the hypothesis on L. From the previous class, what we know is that if we fix U, right? So then there is an AU, right? So for each U, there is an AU such that BUV will be AUV, right? So this is shown by this, right? Since BUV is linear in V, right? So we know that if you fix U, then this bilinear form is going to be linear in V, right? And of course, if you fix V, then this is also linear in U. But first, we suppose that U is fixed, and this is linear in V, and because of the boundedness of B, this is also a linear operator in V. So you can use the Ries theorem to conclude that there is this AU such that BUV is equal to the inner product of AU and V. Now, so this is the first things that we prove. The second thing that we prove is that A is linear. All right, in the sense that if you take U1, U2 in H, all right. So if this is these are two vectors in H, and alpha 1, alpha 2, they are number in R, then you're going to get a alpha 1 U1 plus alpha 2 U2 is going to be alpha 1 a U1 plus alpha 2 a U2, right? So this is linear. And then this can be proved by definition. And the next thing that you see is that, okay, A is bounded. This can be proved by just taking V to be equal to use, right? Test function. V is AU, right? In the sense that if you take the norm of AU, then this is smaller than a constant term U, right? So these are the things that we prove. Now I'm gonna show that A is 1 to 1, right? So this A is a very powerful operator. It is linear, it is bounded, and remember that A is a function. A is a mapping from H to H, right? Because this AU has to be an L2 function so that you can take the inner product between AU and V, right? V is in H and AU is in H. So you can take the inner product of these two L2 functions, right? So this is what we show so far. Now we're gonna have to show that A is indeed a one-to-one, right? So A is one-to-one, right? In the sense that for all of the U in H, for all of the U and U prime in H, if a U is equal to a U prime, then U is equal to U prime. All right, so this is a very powerful property of this A. All right, so this is what we are going to prove next. This is step number 3. Step number three, we're gonna show that if there's two vectors U and U prime in H, and if you have a U is equal to a U prime, then U is equal to U prime. All right. So suppose that we have U, there's U, and there's also U prime, such that a U is equal to a U prime, right? So we're gonna show that U is equal to U prime. All right. So to show that, we will show that U is equal to U prime. Right. So to see this, we have to go back to what? Right. So now I want to show that U is equal to U prime. All right. So to see that U is equal to U prime, I have to go back to what? We have to go back to the definition, right? Definition. So you're gonna know that BUV will be AUV for the V in H, and then you also have BU prime V will be AU prime V for the V in H, right? And now I have to show that U is equal to U prime. Anyone has an idea? No? So now to show that U is equal to U prime, let us do an experiment, right? So we subtract the two. The two equation, right? So 1 and 2. 1 and 2. What do we get? We get B UV minus B U prime V, and this is equal to A UV minus A U prime V, right? So we have to develop this relation, right? This identity. So what can I get from this identity? I mean, how can I develop this? So remember that B is linear. So because B and A are linear. So because B and A are linear, what can I get from the third equation? Right? So remember that B is linear, B is even bilinear, and this A is also linear. What can I say about this relation? So because B is linear, right? So I can subtract U and U prime, right? So this BUV minus BU prime V will be B of U minus U prime V, all right? And then you're gonna have also that AUV minus AU prime V, and this is equal to AU minus AU prime V, all right? And this is AU minus U prime V, all right? So this is coming from the definition of the linearity, right? So because V is linear in both U and V, meaning that if you fix V, this is linear in U. So because this is linear in U, you can group U minus U prime, all right? Now, for the second one, we just proved that A is linear. So this is an inner product, right? So this is nothing but the integral of AU times V dx, and this is nothing but the integral of AU prime V dx, right? So when we subtract the two things, we're gonna get AU minus AU prime V, and because A is linear, we get AU minus U prime, and this is V, right? So now I put these two things together, I'm gonna get B U minus U prime V is equal to A U minus U prime V for the V in H. All right. So we're gonna use this. We will choose a special value of U of V, because this is the test function, right? So this identity is true for all of V. So we will choose a special value of V, similar to the previous lecture. So the previous lecture, we choose V is equal to AU, right? So now we're gonna have to choose a special value of V, so that from the fourth inequality, so that from the fourth equation implies U is equal to U prime. So anyone can suggest for me one choice of V. Right? So I explain again. In this class, we're gonna show that A is 1-to-1, meaning that if A is equal to AU prime, then U has to be equal to U prime. All right. So we suppose the contrary, right? So we suppose that BUV is equal to AUV, and this is true for all of the V in H. And BU prime V is equal to AU prime V for all of the V in H. Now you subtract the two equations, you get BUV minus BU prime V is equal to so this is equal to AUV minus AU prime V. All right. Right. So now, because B is linear in the first variable, so I can subtract U and U prime. So I have BU minus U prime V, right? Surab has a very wonderful answer, right? So Surab idea is the following. Idea. You're gonna choose V is equal to U minus U prime, and this is a correct answer, right? So let me explain again. This part, right? So you have AUV minus AU prime V, right? So when you take the difference between these two guys, because A is linear, you have AU minus U prime V, right? So finally, you have a new equation for U minus U prime, right? So you have AU minus U prime V is equal to AU minus U prime V, right? Right. So from the previous lecture, whenever you see an equation, which is true for all of the V in L2 or LP or whatever, one strategy that you can use is to choose special value of V, so that you can extract some information from this equation, right? So the point is that when you have an equation which is true for all of the test function. You choose special values of the test function. For each special choice of the test function, you can deduce one important property of the solution of that equation, right? So now Surab idea is the perfect idea. So you're gonna choose V to be U minus U prime, and to see what kind of information that we can extract from this equation, right? So we have what? We have V of U minus U prime, V is equal to A, U minus U prime V, right? Now I'm gonna choose V following Surab idea, and I have B U minus U prime is equal to A, U minus U prime, right? All right. Right. So what can I say about this identity? What information? What is the other information that I can extract from this identity? There is a few things about B that we haven't used. What is it? We just used the boundedness of B, right? B, right? So remember that B is bounded. So which means that B UV has to be smaller than alpha UV, right? But there is one thing that we haven't used, coexivity. So how can I use coexivity into this equation? Right? So I have to use this coexivity and I apply that into this equation. What do I get? So this is true for all of the U, right? Is it true for U minus U prime?
Yes.
Yes, so Abdullah answer is yes. Answer is yes. So you're gonna have U minus U prime, right? Is going to be, so there, sorry, there's no absolute value here, sorry. So this is going to be bigger than U minus U prime square, right? So Abdullah is correct in the sense that, okay, I forgot the H. So Surab got it correctly, right? So which means that U is equal to U prime. All right. So following Abdullah, we know that B U minus U prime is going to be bigger than U minus U prime square, right? And then Surab idea is the following. So you plug this into this, you're gonna get beta U minus U prime square is smaller than A U minus U prime, right? But our assumption is what? Our assumption is AU is equal to AU prime, meaning that this is 0, right? So which means that U minus U prime square is going to be smaller than 0, meaning that U minus U prime has to be 0. And then U is equal to U prime. All right. So I explain again. So Surab suggested that, okay, in this equation, you're going to choose a special value of V, right? So whenever you see an equation which is true for all of test function, you choose a special choice of this test function and you try to extract information from that equation. And the information that we can extract is the following. You choose V to be U minus U prime. And then you're going to get this equation, right? So, but when you choose V to be this equation, to be this value, then this, according to Abdullah, this coexivity is applicable. So which means that you have beta U minus U prime is smaller than AU minus U prime, but U is equal, AU is equal to AU prime, meaning that this is 0. So which means that U is equal to U prime. So, and then A is 1 to 1 from H to the range of A is 1, 2, 1 from H to the range of A. A, which is adeno by RA, right? So this means that if AU is equal to AU prime, then U has to be equal to U prime, right? So which means that A is 1 to 1 from H to the range of A. I denote this range to be RA, right? Any questions? Right. So which means that what do we know about A? So A is linear, right? And then A is bounded, right? So A is from H to LA, right? So I is the range of A. So A is linear, A is bounded, and A is 1 to 1. Is 1 to 1. So which is a very nice property. Right. So the next thing that I want to show you is indeed this range of A is nothing but H, right? So step number 4. The range of A is H, right? So I has to be equal to H, right? So basically this A is very nice and very it's a very nice and perfect linear operator, right? So suppose that RA is different from H, right? Right. So this is a vector space, and this is a vector space. Of course, this vector space is included inside the vector space of H, right? So we're gonna prove by contradiction. We're gonna show that RA. We're gonna suppose the contradiction. We suppose that RA is different from H. Of course, RA has to be a member of H, which is L2, right? And then we suppose that RA is a subset of H, but it is completely different from H, which means that, okay, so this means that, right, so RA will be created by a basis EI. I mean, this is the basis of I, and then H will be so basis of H, right? So we suppose that I is a subspace of H, but it is completely different from H, right? So which means that I is expanded by a basis, and H is also expanded by the same basis, including some further vectors, right? Right. So I is a subvector space of H. It is the linear expansion of a basis EI, right? I don't care how many members we have in this basis, but we suppose that H, which is the bigger space of containing A, so because this H is bigger than A, which means that you can have more elements in this basis, right? Right. So now we take a W. We take this. So this I call it UI. So we take UI, which is in H, but UI will be orthogonal to all of the W for all of the W in RA, right? So the strategy now will be that I'm going to take this WI, right? So this WI will be in H, but it is going to be orthogonal to all of the vector that you have in this vector space A, right? And we're going to show that UI is, we will show what? So we will show that UI will be 0, right? Is it clear? I explain again. So you have two vector spaces. This is the range of the operator A, and this is the Hilbert space H, right? You want to show that this vector space is the same with this H, so we prove it by contradiction. We suppose that, okay, this vector space is completely different with H, which means that this is going to be a subspace, a subset of H, but it is not H, right? So which means that this vector space will be the expansion of a basis, and H will be the expansion of the same basis with some other elements, I mean some other basis, right? So of course this UI has to be orthogonal to all of the EI because they are the basis, right? So now I'm gonna pick this UI, and I'm gonna show that because UI is orthogonal to all of the other guy in A, it has to be 0, right? Any questions? It's clear, right? So point number 4, step 4. We pick W UI in H, but UI is going to be orthogonal to all of the W with W is in the range of the vector space, which is the range of the linear operator A. All right. So we will show that this UI is going to be 0. Right. So now there is one thing from this. There's an information we try to extract information from this, right? From the fact that UI is orthogonal to W for all of the W in the range of A, and then UI itself is a member of H, right? What kind of information that you can extract from this kind of thing, right? So you have a vector UI in H. This vector is going to be orthogonal to all of the W in the range of A, which means that the inner product of UI with W will be 0 for all of W in the range of A. So what kind of information that I can extract from this relation? Right? I explain again. So in step 4, what we have to show is the following. So we know that we have a linear operator from H to RA. This is created by fixing Swan-U and then apply Riesz theorem, right? This is a linear operator. This is a bounded operator, and this is one-to-one from H to the range of A. Now, the next step that I want to show you is that this operator is very, very nice in the sense that the range of this operator is equal to H, the whole H. So I'm going to suppose the contrary. I suppose that this vector space is a subspace of H, but it is completely different from H, right? Which means that this range is created by a basis, and H is created by a bigger basis, including this basis, right? So because EI is the basis of this range of A, and then UI is the basis of H, UI and EI, they have to be orthogonal, right? Remember that UI and EI, they are orthogonal because they form a basis for H. Now, UI is orthogonal to all of the EI, right? So I'm saying EI meaning that you have E1, E2, E3, right? So this is not one vector, right? So this is not one vector. This is a set of vector. So this is I from a subset of index, and this is I. This I is going to be in another, this index is going to be in a different set of index, right? So this is a set of index, which means that you don't have only one vector, you have several vectors, right? So because EI with I in this index sets I, and UI with I being in this index set J, this will form a basis for H, right? Which means that UI has to be orthogonal to all of the EI, meaning that UI is going to be orthogonal to all of the W in the range of A, because all of the W in the range of A can be expressed in terms of this basis, right? We will show that UI is going to be 0. Now, I want to show that, okay, if I have a vector UI in H, and this UI is going to be orthogonal to all of the vector W in the range of A, I can show that this UI has to be 0, right? So which means that I have to extract some information from the fact that I have this UI, which is an element in H, and this W. So this W is an element in I, right? Meaning that the inner product of UI with W will be 0 for all of W in I. So what kind of information that I can extract from this relation? So my next question is, what is W? What is the definition of W?
Elements of A.
Right. So so W will be an element in the range of A, meaning that W will be some A of U, right? So this is according to Abdullah, right? So I explain again. W is in the range of A, meaning that W will be A of U for some U in H, right? And this is unique because you don't, because A is 1 to 1, right? So which means that UI A of U is going to be 0 for all of the U in H, right? Because if you pick a U in H, you get AU. AU will be a member of the range of A, right? So what is the range of A? So this is U, so this is H, this is the range of A. So you map a U from H into an AU, AU, which is in the range of A. So the range of A will be the set of all of the AU with U being in H, right? So according to Abdullah, if you replace W by its definition, you're gonna have W is AU with U is in H. Now you replace this definition into this identity, you're gonna get the inner product of UI of A of U is going to be 0 for all of the U in H, right? So I write out the information that I just extracted. So you have UI, which is an element of H, right? And this UI has a very strange property. It's going to be, if you take the inner product of this UI with AU for all of the U in H, it's going to give you 0. Now I'm gonna have to extract some more information from this. What do I have? Remember that here you have something which is true for all of the U in H, right? So from the previous class, or from the first few minutes of this lecture, what did I say? Whenever I see an equation which is true for all of the V or all of the U, you can choose special value for U to extract information, right? So what is the choice of U that you suggest? Right, So Jonathan got it correctly, right? Jonathan, ideas will be to choose U to be equal to UI to extract some more information, right? So now I choose U to be UI. What do I have? I have UI, a UI is going to be 0. Can I say that this is going to give me UI 0? Right? So Jonathan got a perfect idea, right? So Jonathan suggests that, okay, because this equation is true for all of the U in H, which means that if you choose U to be equal to UI, then if you inner product UI with a UI, you're gonna get 0. Does this imply that UI is going to be 0? Basically, we're gonna go back to something that we already proved in the previous few minutes. What is it? Remember that in the previous discussion, right? So what do we say? We have du prime minus u prime, u minus u prime is equal to a u prime u minus u prime, u minus u prime. Then Abdullah said that, okay, because this b is coexistive, you can use the coexistive condition, which means that b u minus u prime is greater than or equal to u minus u prime. And then Surab said, okay, fine. If you apply this coexivity into the equation, what you have is that, okay, you have beta u minus u prime square is going to be smaller than something which is 0, meaning that u minus u prime has to be 0, or u has to be equal from u prime, right? So now we're gonna mimic this proof. All right, so now we're gonna have what? We're gonna have UI, a UI is 0. Can we deduce that UI is 0? Following this kind of strategy, right? You see the similarity? So again, I explain again. So in the previous discussion, right? So Abdullah said that, okay, when you see this a u minus u prime, you can go back to this b. And this b has a very nice property, which is the coexivity. So you have this b is bigger than beta u minus u prime square, right? So you plug this to the left-hand side, then this is going to be smaller than a u minus u prime. This is 0, and which implies that u minus u prime is going to be 0. So now we have something very similar. We have the inner product of UI, a UI is 0. Can you say that UI is 0? Mimicking the previous proof. No? Right? So you see that, okay.
Yes, I think because otherwise we would have something negative, but we have a square of the norm.
Right. So Abdullah suggestion is correct. So what we have is what? What we have is we just replace all of these proof with u minus u prime to be ui, right? So we're replacing the previous proof with ui in the place of u minus u prime. All right, so that's it. Otherwise, the norm of ui will be negative, and this is a contradiction, right? So according to Abdullah. So let us try to copy the previous proof and get what we want, right? So what do we have? You have ui, a ui is going to be equal to what? Right? So our strategy now is very easy. We are going to do the to copy, right? So how can I write UI AUI? So what is UI AUI?
Is the bilinear form of UI and UI.
Right. So this is so BUI UI, right? So according to Abdullah, right? So what is AUI? AUI by definition is coming from B, right? So basically UI AUI will be B UI UI. So this is the suggestion of Abdullah. And now we follow the previous proof. So what is the next step? So in the previous group, what did we use?
Use the coercivity.
Coercivity, right? So Abdullah is correct. You use coercivity. So this is going to be beta bigger than beta UI squared, right? So this is the big B, and this is beta. This is big B. All right. So I explain again. So according to Abdullah, you go back to the definition of AI, right? So in order to go back to the definition of AI, AUI, you have to go back to this B, right? So UI, AUI will be B, UI, UI. This is clear. But this B, UI, UI is bigger than UI square, according to Abdullah, because he was using the coercivity, right? So which means that you have what? You have B UI square is going to be smaller than UI AUI. So now what can you deduce from this identity, right? So you have UI AUI is B UI UI. You apply the coercivity to B. You have this is bigger than UI square. So then you replace this to the right hand side of the equation, right? So which means that this guy has to be bigger than beta UI square. So now you have beta UI square is smaller than UI AUI. So what can you deduce? No? What can you say about, what can you deduce from this identity?
I mean, the left side is non-positive.
Right. So yes, so Abdullah got it correctly. So you use this UI AUI is 0, right? So you use this UI AUI 0, you plug it here, meaning that, okay, the right hand side is 0, which means that the left hand side is positive, meaning that, okay, UI has to be 0 because the norm has to be bigger than 0, so UI has to be 0. And this, we finish the proof, right? So again, I explain again all of the strategy of the last step of the proof, and the almost last step of the proof. So we know that A is from H to A, and this is linear, this is bounded, this is 1-to-1, and even more than that, we want to show that this A will be H, right? So we suppose the contrary. So we suppose that this A is different from H, meaning that there has to be an UI in H, which belongs to the left of the basis, such that this UI is orthogonal to all of the W with all of the W in R, in the range of A. We will show that UI is going to be 0. All right. So to show that UI is 0, it is quite easy, right? So UI is orthogonal to all of the W with W in the range of A, but because W is in the range of A, I go back to the definition. So this is definition only. So W is in the range of A, meaning that W will be A of U with U is in H. So which means that this is equivalent with the fact that the inner product of ui with a u will be 0 for all of the u in H. All right. So now ui is in H, and ui inner product with a u is going to be 0 for all of the u in H, right? So Jonathan suggested that, okay, because this is true for all of the u, we can extract information by plugging special choices of u into this equation. So we choose one special choice, u is equal to ui. So when you choose u to be equal to ui, and then you're going to have ui a ui 0. Does this mean that ui is 0? Yes. So because Abdullah said that, okay, we can go back from this to the bilinear form, right? So ui a ui will be the bilinear form ui ui. Now I'm gonna use the coercivity to show that the ui is going to be bigger than ui squared. But you know that, okay, ui a ui is 0, meaning that ui has to be 0, right? So this is this finish our step 4. So now we know, what do we know about A? A is from H to the range of A, but this is H, right? A is 1 to 1, and this is linear and bounded. So A is a very powerful operator, right? And then the definition of A is what? The definition is A of uv will be B of uv for all of the v in H, and because this is defined for all of the u in H, right? Right. So so now we, and because A is 1 to 1 from H to H, this means that for all of the f in H, there exists a unique uf such that A of uf is equal to f, right? Right? So because A is 1 to 1 from H to H, and A is 1 to 1, right? So what we show is that, okay, because A is 1 to 1, and A is from H to H, which means that for all of the f in H, there is a unique uf such that a uf is going to be f, right? So this is A, so this is H, and this is the range of A. This is 1 to 1, meaning that for all of the u, you're going to have this is u and this is AU, right? So this is 1 to 1, meaning that, okay, if there is another v, then AU has to be different from AV. And because the range of A is H, meaning that if you have an F here, then there has to be, this is V and this is UF, right? So the range of A is equal to F, meaning to H, meaning that if you have an F in this H, there has to be a pre-image UF such that F is equal to A of UF, right? Okay, so so for the next, I think on Friday we don't have class because this is Good Friday, but we can continue the last step of this proof, which is very simple, on Monday. And before that, I want you to do one homework, which is the following. So the homework is the homework is going to be the Clarkson inequality. So this is homework. The Clarkson inequality. So in the previous classes, we know that the Clarkson inequality is true for p bigger than 2, right? So now I want you to prove another version of the Clarkson inequality for p which is smaller than 2. So for p which is bigger than 1 and smaller than 2, you're gonna have f plus g over 2. This is LP. You have p prime This is f minus g over 2 LP, and this is p prime, and this is smaller than 1/2 of f LP p plus 1/2 g LP p, and this is 1 over p minus 1. So p prime is the dual of p, right? Right, so this is remark 3 in the page 97 of Basis. And the due date will be next Friday. All right, I explain again. So in our previous class, I proved for you the Clarkson inequality, which is true for p bigger than or equal to 2. So now I want you to extend this by showing that you also have the Clarkson inequality, but you have to modify the form a little bit. So this form of the Clarkson inequality is the following. You have two functions f and g in LP. P is from 1 to 2, and the dual p prime is the dual p. So now you have a version for the Clarkson inequality when p is smaller than 2, which is f plus g over 2 in the norm LP p prime plus f minus g over 2 in the norm LP p prime is going to be smaller than the norm in LP of f to power p plus 1/2 of the norm of g in LP of p to the power 1 over p minus 1. And this is remark 3 in page 97 of Basis, and the due date will be next Friday. All right. So have a nice weekend. Any questions? So if there's no questions, we see you next on next. You can write it and then send it by email to me. Right? You can submit the homework by writing it and then take a picture and then send it to me on Friday. All right? All right, so see you next Monday. Bye.
Thank you.
Thank you.